Hello everyone, today we are diving into a cornerstone of number theory, Fermat Little Theorem. Named after the famous 17th century French mathematician Pierre Fermat, this theorem provides a deep insight into the nature of prime numbers. Simply put, it states that for any whole number n and any prime number p, the expression n raised to the power p minus n will always be divisible by p, while Fermat often left his proofs for others to find. Today I will walk you through my own proof using the power of mathematical induction. To prove this, we begin with mathematical induction. Our first step is the base case. We test it if the theorem holds true when n equals 1. If we plug 1 into our equation, we get 1 raised to the power of p minus 1, which equals 0. Since 0 is divisible by any prime number p, our base case is confirmed. The foundation is set and we can move to the inductive step. Now for step 2, we make an assumption. Our inductive hypothesis, we assume the theorem is true for a general whole number n. Our goal in step 3 is to show that if it works for n, it must also work for n plus 1. We start by substituting n plus 1 into the equation by applying the Binomial theorem. We expand the term for n plus 1 raised to the power of p. We arrive at our first major equation, labeled here as equation 1. The expansion is the key to unlocking the rest of the proof. We simplify equation 1 by expanding the summation. We notice that the first and last terms of the binomial expansion are n to the raised to the power p and 1. When we subtract the final n plus 1 term, the positive and negative ones cancel out. We then rearrange the remaining pieces to isolate our original expression n raised to the power p minus n. This gives us equation 2, which allows our target expression equal to n raised to the power minus 1 plus a series of intermediate binomial terms. The heart of the proof lies in the coefficient of those intermediate terms. If we look at the formula for a binomial coefficient, we see that the prime p is in that numerator. Crucially, because p is prime and our index k is smaller than p, there is no factor in the denominator that can cancel p out. This mathematically guarantees that every single one of these intermediate terms is a multiple of p. In other words, the entire summation part of our equation is naturally divisible by p. Finally, we bring it all together in equation 3. We know from our initial hypothesis that n raised to the power p minus n is divisible by p. We have just shown that the second part of the equation, the summation, is also a multiple of p. Since the sum of two multiples of p must itself be a multiple of p, we have successfully proven that n plus 1 raised to the power p minus n plus 1 is divisible by p. The induction is